Hello, everyone. Welcome to the third session of this tutorial. In this session, we'll focus on how to deal with time delay in the design of a cyber physical system. This session is presented by Dr. Minshuai Chen and myself. My name is Lai Jun Zhang, a professor from Institute of Software, Chinese Academy of Sciences. Dr. Minshuai Chen is a postdoc from the Aachen University, also one of my former PhD students. I will present the introduction part. Dr. Chen will present the rest parts. According to Radhakisan, Bharati, and Helen Gill's definition, cyber physical systems refer to a new generation of systems with integrated computational and physical capabilities that can interact with humans through many new modalities. The ability to interact with and expand the capability of the physical world through computation, communication, and control is a key enabler for future technology developments. Actually, there are lots of important applications in our daily life of cyber physical systems. For example, automotive, military systems, smart buildings, power generation and distribution systems, avionics, telecommunications, transportations, instrumentations, factory automations. Particularly, many of these systems are safety critical, means any error could result in catastrophic results. So, how can we provide people with a cyber physical system so that they can bet their lives on is a grand challenge for computer science and control theory. Actually, most of cyber physical system can be modeled as a hybrid system as this picture, which consists of two parts, planned part and control part. At the planned side, it accepts control command from the control part together with the data from the environment as input and produce observable state as an input to the control part. The control part accepts the observable state from the plant, but it is present in analog way. So we should transfer the analog signal to digital signal. Based on the input digital transferred digital signal and the computation control model, the discrete supervision can compute a control command. Then also, according to the continuous control model, we can transfer an analog command as input to the plant side. So that is the whole picture of the architecture of hybrid systems. Here, the crucial question is, how do the controller and the plant interact? Traditional answer to the question is that coupling assumed to be time delay. Delay-free means that model dynamics is covered by the conjunction of the individual ordinary differential equations. The switching between the modes is an immediate reaction to environmental conditions. Here we consider an example. The brake subsystem of a car, which is given by Simulink diagrams. So in this Simulink diagram, it is assumed that delay-free coupling between wall components and instantaneous feed through within wall functional blocks. The central questions are here. Is this realistic? So the second question, if not, does it have observable effect on control performance? So further question is, may that effect be detrimental or even harmful? Let's see the first question. Is instantaneous coupling realistic? In reality, in the design of a cyber-physical system, normally, for example, we need to consider the digital control, so that we have to consider the conversion between analog signal and the digital signal, which induce latency in signal forwarding. Also, you see that when digital signal processing, especially in complex sensors like CV, it needs processing time, adding signal delays. Also, for network control, it may introduce communication latency into the feedback control loop, like the car network control. Particularly nowadays, Internet of Things are widely used. In the Internet of Things, harvesting, fusing, and forwarding data through sensor networks may enlarge the time delay by orders of magnitude. So you see that time delay is inevitable, unavoidable. Actually, instantaneous coupling is not realistic. So the question is, what kind of time delay should be considered? The first simple type of delay is a delay reaction, means the reaction to a stimulus from the environment is not immediate. Actually, such a type of delay is easy to model in classical models like timed automata, hybrid automata. Actually, such questioning also can be verified using these techniques. So this question is not discussed today. What we are interested in is so-called network delay, means the information of different age coexist and is queuing in the network when peppered towards target. For example, end-to-end latency may exist sampling intervals and so on by orders of magnitude. Also, not like the continuous time pipeline delay were not efficient like discrete time pipeline delay expressible in our studied models like timed automata, hybrid automata, and so on. Such kind of delay is considered today. Let's consider the second question. Do delay have observable effects? So firstly, we consider a simple example. Let's consider a simple dynamic system defined by this ordinary differential equation x dot equal to minus x with the initial state 1. So its trajectory can be depicted as the left picture. You see its behavior is above the line 0, okay? In reality, such a system may subject to one-time delay. So the formal mathematical model is given by this delay differential equations. Its behavior is depicted in the right picture. You see that the trajectory is fluctuated around the line x equal to 0, which means that we cannot guarantee the system state always keep in the positive side, although the trajectory goes to stable finally. Let's consider a further example. Let's consider the delayed logistic equation. given by these delay differential equations. Firstly, we consider the delay with delay 0.25. So the behavior of the system is depicted as the rightmost picture. You see, the behavior of the system goes to stable very soon. Once we enlarge the delay to 1.52, you see, although the behavior of the system goes to stable finally, but you see that it takes longer time as indicated in the middle of the picture. So also you see that the behavior fluctuates larger, much larger, okay? Furthermore, let's enlarge the delay to 1.65. You see the behavior of the system is never stable anymore. You see that the trajectory is fluctuate larger and larger, never go to the stable. So you see that we can conclude time delays do have observable effects. So the further question, may the effects be harmful? So let's consider a concrete example. Let's consider the path planning of a robot. Suppose a robot can move around a room depicted here. Each time the robot can move 2 steps, any combination of up, down, and the left, right. In this room, there are 2 fixed obstacles here, and one movable obstacle. The movable obstacle can move one step in one time, either right, left, up, or down. So what we concern is that how to synthesize awareness strategy so that the robot can never touch the obstacles. So you see that once we don't consider the time delay, you see that it's easy to synthesize awareness strategy for the robot. The robot just always circle around the obstacle at 1, 2, okay? But the problem is that you see the robot synthesizes the environment through some the sensors. So the sensor may take some time, so which means that the robot may get the environment data, cannot get the current environment data with time delay. For example, here we consider 1 step delay. For this case, the robot still can win the game by 1 step pre-decisions. Similarly, once we consider the 2 steps delay, the robot still can win the game by 2 step pre-decisions. But the problem here is that once we want to synthesize the winning strategy, we need to have extra memory. So which means the winning strategy is not historyless. Once we consider the 3 steps time delay, you see that the robot is not unwinnable anymore because you cannot synthesize the winning strategy for the robot anymore. So you see, yes, delays may well annihilate control performance. In a conclusion that delays in feedback control loops are ubiquitous. The delays may well invalidate the safety stability certificates obtained by verifying delay-free abstraction of the feedback control system. So automatic verification synthesis methods addressing feedback delays in hybrid systems should therefore abundant. But unfortunately, surprisingly, they don't have in computer science. Just in recent years, some first attempts have been done. We just knew a few of them listed here. In this tutorial, we mainly focus on two big issues in the design of a cyber-physical system. Even time delays are taken into account: verification and synthesis. Verification problem is that given a property, a system, and the environment, we need to check whether the system together with the environment satisfies the given property. Once we can prove the property, then we can guarantee the correctness of the system. Otherwise, we should give some the counter examples. The synthesis problem is that given a property and the assumption to the environment, means the model of the environment, we need to synthesize a system so that the system together with the environment can satisfy the property.
All right. Hi there, this is Ming-Shuai Chen. I will take over the screen and walk you through the rest part of the tutorial. Before that, I hope Professor Zhang has already convinced you that time delay is often a killer to the verification and synthesis problem of safety-critical systems. The rest of the tutorial will be mainly based on two sections, followed by some concluding remarks. The first section is on synthesizing delay-resilient safe controllers in a discrete time setting. The second part is dedicated to safety verification of delayed differential dynamical systems. Well, in the first part, I will show how to model the interaction between a controller and its environment subject to some time delays as a two-player safety game. And then on top of this model, we will present an efficient incremental synthesis algorithm that tries to find a safe controller for the controller player. The last part in this section is about a theoretical result on equivalent controllability. For the synthesis part of the work, I have to credit our co-authors, which are Martin Franzler and Peter Nazia-Mozart from the University of Oldenburg, as well as Yangjia Li from ISCAS. Good. Now, imagine yourself as a satellite flying somewhere in the universe. Suppose at some point you receive a command telling you to accelerate a bit, and this command came all the way from Earth. This is obviously not the Earth, but let's assume it is. And then, well, the question is, do you dare take this action to accelerate? Well, if I were the satellite, I don't dare do so, because the transmission of this command signal definitely takes some time all the way from Earth to the satellite. Let's say it takes 10 seconds. And so the control center on Earth actually wanted us to accelerate 10 seconds ago, right? But if the satellite is already running close to some star, let's say, then taking this command 10 seconds later could probably get the satellite crashed, right? So unless you could trust autonomy on the satellite, but if somehow you still want to control the satellite remotely down from Earth, then the control center on the Earth have to somehow anticipate and issue actions earlier. And this is what we call delayed interactions. Good. Now let's look at a very trivial safety game, which is a model for such interactions. But in this setting, let's assume it's delay-free first. Well, in this game graph, you see two types of nodes. The circle node is a state where player 1 has to make an action. Let's say he can take an A action, then the game goes to a state A1. And this box state is where player 2 has to make a decision or make an action. Now he can choose U, so we arrive at another state for player 1. So the game is played alternately until some player wins. And the winning goal for player 1 in this example is to avoid this A5 state, which is an unsafe state, by appropriately choosing actions. Well, in this example, there is a winning strategy for player 1, which is always to play action A, except in the state E3. Why this is the case? For example, let's look at state E1. Choosing A leads the game to an safe state A1, and at A1, player 2 doesn't have any choice except U, so he has to choose U, and now we arrive at E2. In this setting, again, according to the strategy, we have to choose action A. Now we goes back to A3, and again, player 2 doesn't have much choice, so we will end up in E1 again. And by playing according to this strategy, player 1 will never visit A5, right? So this is a winning strategy for player 1, sorry. There are some nice properties for safety games in this model. For example, determinacy, meaning that either player 1 or player 2 has a winning strategy. While memoryless means that such a winning strategy doesn't need any memory. So you don't need to memorize the play history in order to win. Later on, you will see how these two properties are different in the delay setting. Good. Now first, for a rather general picture of delay games, suppose we have two players, the ego player and the adversary player. They are playing a game at some game arena here modeled by some game graph. Well, in this tutorial, we always assume that the adversary player has perfect information of the game state information. That means player 2, so this adversary player, can observe the game states immediately, make some actions, and execute the action immediately. But for the ego player, which is the controller in our work, delays could happen. For example, in the perception channel, the state information could take some steps of time until it arrives at the ego side. For example, in this here we have 5 time units of delay. Well, delay could also occur in the actuation channel, meaning that an action or a decision made by the ego player takes some units of time, in this example 5 again, until it could really be executed or takes effect in the game graph. But a nice observation here is that whether delay occurs in the perception or in the actuation channel doesn't make an observable difference if we are sitting, say, at the interface of the game graph. So this gives us a nice property that we can always consider one direction channel of delays. Well, for the case where we have, say, m time units delay in the perception and n time units delay in the actuation, we can simply combine them as a one direction delay with m plus n time units. Good. Now, such an observation yields the fact that there's an obvious reduction of such delay games to a perfect information game, as we just saw from previous slide. But notice that such a reduction is dedicated to the ego player. We don't have any delay for the adversary. Good. And how the reduction looks like? It looks like as follows. So we simply take the product of a shifted register with the game graph, just like what we do in automata production. Well, this product gives us a nice thing. which is safety games under delays, can always be solved algorithmically. Why? Because after this reduction, there's no delay anymore. And we have a delay-free game, and there is already decision procedure for computing, for checking whether player one is winnable or not. And this is done usually by computing the fixed point of a set of unwinnable states. And then if at the end the initial state is unwinnable, then the player doesn't have a winning strategy. Okay, but this reduction also has a negative side, which is obvious because such a reduction may incur some blow up of the state space. And in this setting, the blow up would be exponential in the magnitude of delay. So later on, you will see an efficient synthesis algorithm that tries to reduce this blow up. Now let's come back to the simple safety game we saw earlier, but this time we have delays. Recall that for the delay-free setting, we already have a winning strategy for player one, right? Like this. Now imagine we have a one-step delay. What does it mean? It means that every action made by player one has to take one time units until it can take effect. And from another point of view, the action that takes effect at state E2 is actually pre-decided one time unit ago at the box state A1. So now we label the box state with the strategy of player one. So now the strategy for state A1 is A, means that at state A1, player one already foresees the decision one step later, and he decided to perform an A there. That is perform an A at state E2, right? One can easily verify that this is a winning strategy for player one. But now again, let's increase the delay a bit to 2 steps. Now things get a little bit different. Why? Because let's, for example, consider the strategy at state E2 and E3. So both of actions that will take place at E2 and E3 have to be pre-decided 2 steps ago, right? That is at state E1. In order to make such a decision safe, we have to guarantee that we won't take this B, neither this A here. So we have to take the intersection of the safe actions at E2 and E3. But the intersection of the safe action A and B is an empty set. That means we don't have a winning strategy for player one if we do so. However, if player one still wants to win, there is a way, that is to introduce some memory for him. For example, if we have the memory that at state E1, player one actually chose A, then at E2, we will know that we are at E2. So we simply choose A. However, if the memory tells us E1 chose B at this step, then 2 steps later at E3, we can only choose B. This is what the strategy here says. At state E1, if an A was issued 2 time units ago, telling that player E1 will choose an A here, then 2 times units later, which is at E2, player A will choose an action A, and B is similar. So now you see there is indeed a winning strategy for player one, but he needs some memory. This is the different thing with the delay free setting. Good. Now here is an incremental synthesis algorithm that we proposed based on a basic observation saying that a winning strategy for a delay k prime, which is a bit larger, can always be utilized for a safe win on the delay k. Well, the consequence of this observation is that a precision is winning for a smaller delay k is a necessary condition for it being winning under a larger delay k prime. All right, I hope this is somehow obvious to you, because if a player wants to win under a larger delay, he first have to win under a smaller delay. All right, then the basic idea of this incremental synthesis is that we increase the delay step by step, and in between it gives us the possibility to remove all the states that are already unwinnable. So for the first step, we synthesize a winning strategy for the delay free setting. And as I said, we already have an algorithm for that. Well, the next step is to lift the delay k to k plus 1. And this step is important because to come up with the strategy for k plus 1, we can always use the information that is already encoded in the strategy of delay k. And later on, you will see how this information is used. And then we also remove states where this does not succeed anymore. Now we can repeat the process until we are able to find the delay tolerance strategy for player 1, or we find that the initial state turns lossy already. Now a little bit closer look at the algorithm. So we first generate a maximally permissive strategy for delay k equals to 0. Here by maximally permissive, I mean player 1 can take whatever actions he wants, as long as these are safe actions. So a strategy for player 1 will, at every state, will be a set of actions instead of a single action. All right, so the algorithm to lift from delay k to k plus 1 in two cases. So for the first case, when the current delay k is an odd number, this means that player 1 has to pre-decide at a box state, for example, a5 here. And since we already have the strategy for delay k, and this strategy tells us at state e3, we have a pre-decision ACE, and these actions are all safe. And similarly for state e4, we have safe actions B, C, E, F. Now, in order to lift the delay to k plus 1, we have to label the box states with the strategy for player 1. And how to do that? We can simply take the intersection of all those of these two safe sets of actions, which are C and E. Okay, so C and E here mean that at state A5, player 1 can pre-decide already that k plus 1 time units later, I will play either C or E, and both of them are safe. Okay, here's another case. If the current delay k is even, now this means player 1 has to make a pre-decision at his own state, say E5 here. And the difference is that in this case, player 1 can actually decide which action to choose because this is his own state, right? And so for sure he has to remove an action that goes to an unsafe state, but for the other actions, the only thing we need to do is to prepend such an action, say A here, to the play history, and here we have to prepend C to the play history. and just to keep track of the game history. And now we can repeat the whole process until we are able to find a delay tolerant safe strategy, or we find that player one is not winnable anymore. Good. We have a prototypical implementation of the incremental algorithm, and here we did some experiments. The benchmarks are from the escape game between the robots and the kid you have already seen from previous slides. We did some comparisons. So here the red block indicates a explicit reduction-based implementation. So in this red part, we simply take the product of the shift register with the game graph and then solve the delay-free game. As you can see here, in many cases, the implementation failed to find a winning strategy or prove unwinnability. On the right, this blue block is our implementation based on this incremental algorithm. And it definitely performs better because in all those cases, we were able to find a winning strategy for player one. And here the dash means that we are able to show that the player one is not winnable anymore. And also in the last column, you see the percentage of the state space that we can remove during this incremental synthesis. And this is actually the reason why we could do in an efficient way. And then we also did a comparison with the state-of-the-art synthesis tool called CPS, which implements a symbolic representation of the game arena. So in this block, we also first do the reduction and then solve the delay-free game with this state-of-the-art tool. Now, in this case, it performs definitely better than the naive implementation. But when delays go larger, say at 4 or 5, our implementation is able to synthesize a winning strategy or a winning controller in a couple of seconds. But this is not the case for this tool. So this tool doesn't scale much better in the delay setting. Okay, now until now, what we have seen is very restricted setting where the delay is fixed. And by such a fixed delay, if you imagine the shift register, all the information in the register will come in order, right? But this is often not a practical assumption, because in some scenario, the information in the observation or in the actuation queue, in the register doesn't actually come and go in order. So this gives rise to the question, how about non-order preserving delays? For example, in this figure, the observation 61 of the state information can actually come earlier than the observation 60 and 59. But this actually results in a very surprising fact that such an out-of-order delivery of the observation merely reduced effective delay, and it turns out to improve controllability. Well, the intuition is that whenever we have an observation arrived earlier than in the strict delay case, we actually have more recent state information available earlier, right? And this amount of information may help us to come up with a controller that is winning for player one. So you see, in this case, the effective delay is actually 2, but in the order preserving case, the delay is 5. So in a qualitative setting, the worst case of out-of-order delivery is actually equivalent to the order preserving delay k. And if we go to a stochastic setting, it's even better because the expected controllability is even better than the strict delay case. Okay, another setting is about message loss. Say there could be a possibility that some observations will never be received by player one, and how we can deal with that. Here's an illustration of the idea. Suppose we have two state informations, pi6 and pi8, which get lost, but our incremental synthesis actually gives the possibility to tackle this setting, because let's say when making a decision, we can always make two backup decisions subject to delays. So sigma 2 here is actually a safe action or a safe set of actions that can be played if two delays are in the game. And sigma 4 here is a safe strategy subject to delay 4. So we make these two predecisions and we cache them in a queue. This queue is useless if player one always have the most fresh state observation. However, whenever a message is lost, we can simply retrieve from the queue this action sigma 6, which is safe to play at this time instant, even if we don't have access to the current state information. And similarly, this sigma 8 is safe to be taken at this time unit. So as you can see that as long as the number of consecutive message loss is finite, we can always make pre-cache backup actions that are safe to play, even though those messages are lost. So the conclusion is the controller can still win a safety game in the presence of bounded message loss, leveraging delay resilient strategies by our algorithm. Good. Now the last slide of this part. This is a theoretical result on the equivalence of qualitative controllability. The whole theorem looks horrible, but the intuition is that if there exists a winning strategy under an exact delay of delta, then we can show that there also exists a winning strategy under any out-of-order delivery with a maximum delay of delta. And furthermore, there also exists a winning strategy even there are messages get lost, but the number of consecutive lost messages is no larger than half delta. Well, for more details, you can find in our journal paper listed down here. Okay, now we are moving to the second part of the tutorial, which is dedicated to safety verification of delayed differential dynamical systems modeled by delayed differential equations. And delayed differential equations, DDEs for short, is a formal model for delayed feedback control. And here in this setting, everything is continuous, so time is continuous. And all the results I'm gonna present is under the cooperation with Martin Franzler, Peter Nasser-Mozart from the University of Oldenburg, as well as Yangjia Li, Shenhua Feng, Bai Xue, and Liang Zhou from ISCAS. Okay, so first of all, a little bit history on delayed differential dynamics. The study of delayed coupling in differential dynamics dates back to the 1920s when Vito Volterra in his study of the predator-prey dynamics, formulated a rather general differential equations that incorporates the past state of the system. The intuition is that, for example, a certain species needs some time until they can grow to the age for reproduction. So there's a time delay in the model. And the theory of delay differential equations was later popularized by, say, Bellman and Cook, together with another group of researchers. Here's a quote from their book. It says that detailed studies of the real world impel us, albeit reluctantly, to take account of the fact that the rate of change of physical systems depends not only on their present state, but also on their past history. This gives rise to the following model known as delay differential equations. Here I highlighted the difference with an ordinary differential equation. Here x is the system state, which is a vector, and x dot is the temporal derivative with respect to time t. And the difference here with an ordinary differential equation is besides xt, the current state, it also depends on some past states. Say this term xt minus r1 is the state r1 time units ago. Sorry, in the continuous setting is r1, let's say seconds ago. And it can have multiple delays from r1 up to rk. Another difference is the initial condition. So in an ODE, if we have an initial point, then we can propagate until we get the solution of the system. However, in delay differential equations, we have to provide an initial function defined on the interval from minus r max up to 0. And here r max is the maximum delay through r1 to rk. Now, with further assumptions on some Lipschitz continuity condition, we can get a unique solution or trajectory denoted in this way. So this chi is the solution at time t, starting from the initial function phi. By this slide, I'd like to argue why DDEs are harder than ordinary differential equations. And this is fundamentally because in ODE, the evolution of the solution is actually a propagation of some state snapshots. All right, because starting from a single point, a single state in the state space, you already have the entire solution. However, in delay differential equations, you can see the solution is sliced in different fragments, and every fragment is the length of the fragment is the length of the delay. So instead of some snapshot state, a state in DDE is actually a functional state. So you have infinitely many states or many points on one functional state. So DDEs actually encode infinite dimensional memory of the past. So try only if infinite state no longer is scary enough to you. Okay, now I'd like to recap the safety verification problem for delay differential equations. Suppose we have this blue region, which is the set of initial functional states for DDEs. And the verification obligation is to guarantee that every system trajectory or solution originating from this blue region will never enter the unsafe set of states. And the union of all those trajectories is the reachable set, which this reachable set is often intractable, especially for nonlinear hybrid systems or dynamical systems, just like ordinary differential equations. And that's why there are a lot of work trying to approximating such a reachable set. And the system is said to be T-safe if no trajectory enters this unsafe set of states within a bounded time interval from r minus r up to t. especially when this holds for the entire time horizon. We will say that the unbounded safety is achieved and denoted by infinite safe. Okay, now in what follows, I will first show two methods on dealing with bounded safety verification problem. The first method is called simulation-based verification, and here's a general framework for this method. Suppose we are given an initial set, which is the gray region here, and the framework is to first partition such a set into some smaller, say, circles. And then for each this small circle, we do a simulation from the center of the circle. And this gives us this dashed curve. And in the meantime, we bloat such a solution by some, say, sensitivity analysis. And what we can get is actually an over-approximation at time instant t of the exact reachable set, which is the light gray area. Now, if we are able to do the same for every such circles, then taking the union, and the remaining thing to do is to check whether the union is disjoint with the unsafe set of states. But since this is an over-approximation, so it could be the case that the entire over-approximation intersects with the unsafe set of states, so we cannot claim anything there. Now, in that case, we can refine the partition with smaller and smaller circles, and hopefully we are able to verify safety of the system. Okay, now in this general framework, we proposed a validated simulation-based verification technique for delayed differential equations. The idea is first to do numerical simulation for every of such partition. And then we incorporate some local error bound analysis, which is the green region that bound all possible reachable states from this single point. And this too is because the simulation is always subject to some numerical errors. And after that, we do the sensitivity analysis, and we are able to come up with the red area that encloses all the possible reachable states starting from this circle. Again, we do the same for every partition, and we can verify or refuse some safety property, but not always. You will see later for some examples. This is an example known as delayed logistic equation. It is used to model the population size of one specific species. Here, R models the delay subject to the reproduction age and due to some limited source of food. In this figure, you see a simulation and the over-approximation of the entire reachable set. Now let's say we have a unsafe region which is above 1.6 in the system, in the state space. And we find here at this point the entire over-approximation follows within the unsafe area. And by that, we can claim that the system is unsafe. Okay, and then here's a safe example on the same system. Suppose we are interested in the reachable set starting from the initial set of states, which is from 0.5 to 1.5. And then we first do a partition. It gives us two sub-intervals. One is from 1 to 1.5, and the other is from 0.5 to 1. And for each of them, we do the same simulation-based over-approximation. And here we find that the over-approximation intersects with the unsafe set of states. And in this setting, we cannot claim anything. What we can do is to refine the partition. This gives us this two sub-figures. So for the upper partition, now we are able to verify that this over approximation is away from the unsafe set. And the same holds for the lower approximation. For the other partition at the initial stage, the same goes as follows. So by 6 rounds of simulation, we were able to prove safety of the system. Here's another example from biology. Well, this is a phase plot, and the red dashed circle is the initial set of states. Here you can see that the trajectory actually converges to some equilibrium. Now, in this example, we were able to verify safety by 17 rounds of simulations. Okay, now a disadvantage of this method is that we still have to guarantee that every state in the initial set or in the finite partition of the initial set is safe, right? We have to take care of their evolution along time. And this is also a common problem for almost every reachability-based verification of hybrid systems. And that's why we propose another approach, which is based on boundary propagation. Now, the idea is that we first came up with a condition with an upper bound listed here. It's a little bit complex, but I will not go into the details. So the nice thing is that we can show if the delay term R is no larger than such an upper bound, then the solution of the DDE has some nice property called homomorphism. And this homomorphism property guarantees that given an initial set X, every point on the boundary of such a set after the solution mapping or after the propagation of the flow field, it remains on the boundary of the reachable set. Okay, so there would not be a case where a point on the boundary of the initial set goes into the interior of the reachable set. This is not going to happen. So with that nice property, we only need to deal with all those points on the boundary instead of the entire points within the initial set. So if we can compute an enclosure of the reachable set's boundary in this way, then we are able to compute the over approximation of such reachable sets, which is the blue area, by simply including the enclosure using some, say, convex shapes. And in the meantime, we are able to compute an inner approximation of the reachable set, which is the yellow area, by excluding the enclosure. And notice that under approximation is also an important concept in the verification of hybrid systems because it often helps us to falsify some safety properties in hybrid systems. Good. Now you have seen 2 approaches for bounded safety verification. What comes next is another 2 methods on unbounded safety verification. And this is simply by taking some stability certificate, and then we are able to show that the unbounded case can be reduced to the bounded case. Good. Now for the first method, we consider a rather simple form of delay differential equations, which is this negative feedback system. Notice that here we only have the delayed or the past state. We don't have the current state in the equation. The idea is try to first, it's based on the following observation. So if we have, let's say if we integral the flow field F on the delay interval from n-1r to nr, and then what we get is actually the Taylor series for the segment solution in the next step. Okay, so this is also known as the step of methods in solving delayed differential equations. But this method is definitely not efficient because the degree of the Taylor series grows indefinitely and rapidly. So computationally it's intractable. It also lacks means of analyzing unbounded behaviors thereof. So that's what motivated us to consider interval Taylor series of fixed degree, because by that the degree of the interval Taylor series is fixed and is tractable if the degree is low enough. It also permits us to perform bounded model checking techniques therein, but the bad thing is still there's no immediate means for unbounded analysis to tackle that. You will see how we can extract and operate computing the next interval Taylor series from the current one. So this actually gives us the possibility to reduce a delayed differential equation to some discrete time dynamical systems. And yeah, so here I will show the basic technique by an example. Recall this simplest negative feedback system where the derivative of x is minus xt minus 1. And the initial condition is a constant function equal 1 here. So if we do the segment-wise integration in this step, say on the time interval from 0 up to 1, this is what we get. And by reformulate a bit, what we have is a relation between the solution fn to the solution fn minus 1. Okay, now apparently fn is a polynomial of degree n, but if you really compute this, you will find that after a day the degree gets to 80,000, so it easily gets intractable. So this is why the interval Taylor series come into the picture. And the idea is, so we first fix a degree for the Taylor series, let's say 2. Then this gives us a template, a polynomial template up to the degree 2. Okay, now here every coefficient in this template, say an0, an1, or an2, is an interval. And this interval is used to enclose the approximation error. So you can imagine this Taylor series template as an kind of an enclosure that encloses the solution or the reachable set. Okay, now in order to compute the next step, we need the derivatives in the Taylor series, and this can be simply done by taking one step differentiation here. Now substituting these two derivatives here in the template for the next segmentation, we get this this polynomial here. But remember that every segmentation admits the same form of the template. So that means we can simply do a coefficient matching of this this Taylor series with this template. What we get, this is what we get. This is a discrete time invariant parameter linear operator, where all those coefficients are now the states of this linear operator. Notice that here an plus 1, an plus 1, and here an are all intervals. Now by further replacing this term with a constant interval 0 to 1, what we get is actually a time invariant discrete time linear system. And this is nice because we already have a lot of efforts that that are able to verify safety or stability of such a linear operator. In order to further deal with unbounded safety verification, we somehow have to consider stability of the delay differential equation. The observation is that if, let's say, the global solution X to a DDE stabilizes asymptotically, if the solution of all the segments Fn converges to 0, right? And this holds if and only if the coefficients an, which is the state in the discrete time linear system, if all those coefficients converge to 0. Now the consequence of such observation is that we can reduce stability verification of DDEs to the stability verification of this interval linear time invariant system. And in what follows, we find some nice results on doing so. For example, we can synthesize some Lyapunov function witnessing the stability of this linear system, which in turn guarantees stability of our delay differential equation. But due to limited time, I won't go into details of this result here. But the general approach is as follows. So in order to verify unbounded safety, let's say always staying in the set of in S, which is the set of safe states. This can be accomplished by several steps. So first, we generate a Lyapunov function for the linear operator by this result. And then we try to compute a barrier value, such this barrier value is C, such that this formula is unsatisfiable. Now, if this is true, what it tells us is if we were able to find such a C that this formula is unsatisfiable, then the Lyapunov function does not exist C implies the fact that the solution is always safe. So it stays always within the safe set of states. Great, now we need some further calculation because we have to reduce the unbounded safety to bounded one, and this can be done by calculating a safe bound, dm here. And with that, we were able to claim that the maximum steps we need to compute the Taylor series is k. So k can be calculated in this way. Then if we were able to verify safety of the system up to step k, then we can claim safety of the system over the entire infinite time horizon. Now, what remains to be done is to pursue bounding model checking for the first k steps, right? And this actually guarantees unbounded invariance. Good. The same technique also applies to multi-dimensional polynomial DDEs, where x is now a vector and g is a vector-valued polynomial. And all those listed here are basically similar to what you have seen by this simple example, so I will skip here. Again, in the multi-dimensional case, we have a multi-dimensional linear operator here. So we can use the same group of techniques. Good, but one disadvantage of this method is that it can only deal with the DDEs of a very restricted form, That is the negative feedback shape, where you cannot have current states in your DDE formulation. So now I will present a more general approach, and this is based on linearization and spectral analysis. Now let's first consider some linear delay differential equations written in this way, where A and B are matrices. A classical result of spectral analysis makes use of this characteristic equation. It says that this equation is that the determinant of this formula is 0, and this formula is actually lambda I is the identity matrix minus A minus B times e to the power of r lambda. Now, the magic of this characteristic equation is actually as follows. So this exponential part is what differs from the ordinary differential equations. It comes from the delay part here. All right, and if we can solve this characteristic equation and plot all the roots of this equation in the complex plane, we get something like this. So every star here is a root to this characteristic equation in the complex plane. Well, a nice thing is that if all those roots have negative real part, that means we can find some negative bond alpha here, that all those roots lie on the left-hand side, then this linear system is actually exponentially stable. In a more formal way, so if all the real parts of the eigenvalue, which is the roots to the characteristic equation, is negative, then the solution of the system can always be bounded by some constant k times e to the power of alpha t. And alpha here, as you can see in the picture, is a negative constant. So a negative as the exponent gives a exponentially decreasing bound on the solution, right? And this holds for every possible initial condition, in this case an initial function. But in classical stability analysis of DDEs, this is only a qualitative result saying that, yeah, it is exponentially decreasing, but how fast? It doesn't say anything, because it only says there exists some k, but we don't know how to compute such a k. In order to enable automatic verification of the differential dynamics, we somehow have to give an explicit way to compute this constant k and alpha, such that we get an computable upper bound on the set of reachable states. How we can do that? Well, for linear differential equations, we provided a way to compute the constant alpha and a way to construct the constant k. With that, we actually have an over approximation of the reachable set here as the gray area, and this curve is, you can see the upper bound k times e to the power of alpha t. Well, a nice thing here is that this gives us the possibility to compute the intersection of this over approximation with the boundary of the unsafe set. Let's say all the states beyond this two red line are unsafe. Then if we can calculate T star here, then every solution after T star is no more of interest, because it already falls within the safe area, right? And this is the key, that we can reduce the unbounded safety verification problem to a bounded one, because now in this case, we only need to consider a bounded verification from t equals to 0 up to T star. right? That is what it means. Infinite safe is equivalent to T safe for every T larger than this threshold T star. Good. Now for nonlinear delay differential equations, we use the technique of linearization here. For example, for a possible nonlinear F flow field, we can write it in this form where A and B are the Jacobian matrices with respect to X and Y respectively. And then G here is the higher order term that makes it nonlinear. Well, what we can do is first to drop this higher order term, and then it ends up in a linear equation, what we call the linearization. And then for that, again, if the eigenvalue of this system all have a negative real part, now the original system is locally exponentially stable. So formally, it is written this way. What does local mean? It means that there is a certain distance from the origin, let's say, such that for all possible initial functions starting within such a region, the solution to DDEs can always be bounded again by an exponentially decreasing upper bound. So similarly for nonlinear differential equations, by our approach, again, we are able to compute alpha, which is an upper bound on the real part of all the eigenvalues, and then to construct the constant k, as well as the constant delta, which is the, you can say, the region of attraction, such that starting from such a region, the solution will always be bounded by an exponentially decreasing enclosure. Now, again, we compute T star for the linearization. But in this setting, we have to use some bounded verifiers for delay differential equations to guarantee that the solution will first enter such a basin of attraction, because this T star tells us if we start from within delta, the only thing we need to consider is for an interval up to T star. But using the bounded verifier, we can first guarantee that after some T prime amount of time, the solution, the reachable set is already contained in such a delta distance. Now, by taking by adding T prime and T star, we were able to reduce again the unbounded safety to bounded safety. This is an example for the earlier presented population dynamics. So using some bounded verifier, we were able to claim that the unbounded verification problem can be solved if we can show bounded verification up to T prime plus T star here. An interesting thing is here, as you can see in the long tail, this is what the bounded verifier gives us as an over approximation of the reachable set. As you can see, after some time, it diverges fast. So this over approximation cannot be used for the unbounded verification of DDEs. But it still helps us to find the time threshold T prime such that the entire reachable set is contained in the basin of attraction delta. Great, and now I will show the methods by some example. The first one is a non-polynomial one, where we have some rational functions as the flow field. And in this case, we first do the linearization. This is the linearized DDE. And then by our method, we were able to compute the crucial constants alpha, k, and delta. And in this example, t star is 0. While by a bounded verification technique from COF 18, with the Taylor model of order 5, we were able to show that the entire reachable set is already, the entire over approximation is already contained in this delta range at this time interval from 25.45 up to 25.95. And together with the fact that the entire over approximation from minus 0.5, which is the delay, up to t prime plus t star is disjoint with the unsafe set. Now, these two facts together use the infinity safety of the original non-polynomial delay differential dynamics. Good. A short comparison with existing methods for unbounded verification. So this method first allows immediate feedback, that is XT. It also allows multiple delays in the dynamics, comparing to the previous method I introduced, which is dedicated for the negative feedback system. Also, in this method, we don't have anything for like polynomial templates, which are, however, needed in a lot of works. For example, for the Taylor models, for Lyapunov functions, for barrier certificates, we always have to set a template and then try some constraint solving techniques to find some instantiation of the parameters in the templates. But in this technique, no such thing is needed. The last advantage is that this method allows delay dependent stability certificate. Because as you saw from the enclosure in the previous picture, it is dependent on time, right? It changes over time. Other than that, there are some other existing results which assume absolute stability. That is a rather restricted condition on the original system that have to guarantee stability for any arbitrary larger delays. And this is often a non-practical assumption. But there's also some disadvantage of this method because it is confined to differential dynamics featuring exponential stability, as you saw. So investigation of more permissive forms of stability, say asymptotic stability, which may admit a similar reduction-based idea, is subject to future work. Okay, to wrap up, we are facing increasingly widespread use of networks distributed sensing and control, where substantial feedback delays affect hybrid control schemas. And in particular, delays may affect controllability and control performance in both the discrete and the continuous setting. What we have presented in this tutorial includes safety games, which is a model for delayed interaction with for delayed interaction for a controller with its environment, and on top of that, an incremental algorithm for efficient controller synthesis. And later on, I introduced the bounded safety verification methods for delayed differential dynamics, and we extended them to unbounded verification by incorporating some stability criteria. There are tons of future directions, but what we planned to explore includes controller synthesis for delayed hybrid systems in the continuous time setting, as well as DDEs featuring state-dependent or stochastic delays. We also have the plan to move to the hybrid setting, let's say hybrid automata comprising DDEs instead of ODEs, or hybrid automata combining delayed, continuous, and discrete reactive behaviors. And the last but not the least, invariant generation for time-delayed systems. Good. Now I'd like to use the last slide, which is a cover of a poetry collection from the Belgium, and there's an interesting story behind. So there's a group of poets who were trying to compose poems during their travel by some train. And an interesting fact is that they find out the longer the train is delayed, the higher quality their poems would be. So this gives rise to this cover of the collection of the poems. And I think this is super pertinent to this tutorial. So hurry for delays. And with that, I'd like to conclude this tutorial, and we will be extremely happy for questions at the Q&A session scheduled on 1st of December, RTSS Hot Topic Days. Thank you. Bye-bye.